All right, this is the first video on the kinematic equations. There are four kinematic equations, and I'm kind of covering them in kind of arbitrary order. There's no particular reason why we did the first one first. It's just we did the first one first. And the first one is a combination of two different ways that we can calculate the average velocity of an object. The first way we can find average velocity is the one that we learned in our first unit. It's the displacement of the object, or delta x, divided by the elapsed time, or delta t. Second way we talked about when we began this new unit is just to calculate an average. If you have two test grades and you want to average them together, you would add the two grades and divide by 2. Same thing can be done with the velocity. If you know the final velocity and the initial velocity of your object, you can add those two things together and divide by 2 to get the average. What we did is we took these two expressions, the displacement over time and the VF plus VI over 2, and we made them equal to each other. And then we solved it for delta x. And the way we solve for delta x is by multiplying both sides by delta t. So delta x equals, we took this expression, instead of saying this divided by 2, 1/2 times VF plus VI, mathematically the same thing, times delta t. And that was the first kinematic equation that we learned about in class. And it does some things that our other equations couldn't do independently. If we know the final velocities, initial velocities of an object, and how long it was traveling, we can figure out how far it went. We can figure out how much time it takes something to travel a certain distance given a final velocity and initial velocities. It gives us a different way of looking at some of these motion scenarios that we talked about, that we learned about in class. It makes our bag of tricks a little bit deeper, allows us to analyze more scenarios from different kind of motions. All of this is linear, so we're still talking about objects that are moving in straight lines in single directions. Because of that, you'll see the words distance and displacement used interchangeably, because when an object is moving in a straight line in a single direction, distance and displacement are the same. You'll see the words velocity and speed used interchangeably, because again, when an object is traveling in a straight line in a single direction, the speed and velocity will be the same. So don't be surprised when a question talks about speed, and what you're really doing there, what you're really using it as is velocity. It's not a mistake, it's just because they are the same in these situations, in these scenarios. So let's take a look at a couple of examples of what these problems look like. Let's say we're talking about a plane, a Boeing 737. Boeing 737 needs to reach a speed of about 67 meters per second to take off. Let's say that this Boeing 737 is at an airport that has a 2,500 meter long runway. We're going to calculate how long the pilot has to get the plane up to speed from rest. We're going to figure out how long the pilot has to get the plane up to speed from rest before running out of runway. So let's take a look at the numbers we have, always where we start, trying to figure out what this and that are. 67 meters per second, that's a speed or velocity unit. And it even says it in the equation, speed of. Again, we use the word speed and velocity interchangeably in this because they're a straight line motion. So speed and velocity are the same. This would be our final velocity because we have to reach this speed. We have to get up to that speed. Our initial velocity is right here. It's not a number, so it's not expressed that way in the question, but we are accelerating from rest, so our VI is 0. Meters is a distance, so that is our delta x. We want to know how long it takes. That's time. So we go through, we figure out what our numbers are, what we have to work with. We figure out what we're looking for. That way we can plan what we're going to do. We don't want to just start putting numbers in calculators before we know what to do with them. Our equation, delta x equals 1/2 VF plus VI times delta t. I know that's the equation I use because that's what fits the variables I have. This is one of the things that will become, I guess, the biggest challenge as we wrap this unit up is picking out which of the 4 kinematic equations we're going to use to solve our problem. And again, that comes down to looking at what you're given, what you're trying to find, and then picking the equation that has those same variables in it, or has most of those variables in it and something else you can find given those numbers. It's that problem-solving thing. It's the reason why physics is challenging and why colleges really look for it on transcripts. So let's substitute. 2,500 meters equals 1/2 67 meters per second plus 0 times delta t. So first thing I'm going to do is simplify this by doing 1/2 times 67, or 0.5 times 67. That's 33.5. Still meters per second because these are the same. Times delta t. It was 2,500 meters. And I'll divide both sides by 33.5 to isolate my variable. Opposite operation, since we're multiplying, we divide. Everything cancels over here. Writing it out the way we want it, variable first. Delta t is 2,500 meters divided by 33.5 meters per second. That's 74.6. And again, I'm just arbitrarily rounding because we're not using significant figures. Meters cancel. Seconds in the denominator of the denominator move up. So 74.6 seconds would be the maximum amount of time the pilot had to get the plane up to speed before running out of runway. Now that's a straightforward one where we're not having to do any kind of unit conversions before we start. Unit conversion is something that does happen quite a bit with this equation. And that's because the units that we have here for our velocities, the time units in these velocities have to match the time unit that we're using in the equation. That's the only way we'll get proper unit cancellation. So we need to make sure that we're careful of units, looking at units closely when we do these kinds of problems. Let's take a look at an example of where we have to do that. So let's say we have a car, and that car can go from 0 to 60 miles per hour. Let's go ahead and put the unit on it. In 7.2 seconds. How much road would it need to accelerate from 0 to 60? Or how far will it travel? Again, the first thing I do is go through and figure out what all these numbers are. These are miles per hour, so those are speeds or velocities. The 60 mile an hour would be my final velocity because that's where I'm going to. 2 always tells us where we're going to end. And the 0 miles per hour will be my initial velocity because of the word from. That's where I start. So VI is 0 miles per hour. VF is 60. That's my time. Seconds. And I'm looking for the amount of road it'll travel down, how far it will go. I'm looking for delta x. So again, same way I started the last one. Now when I look at these units, I see that I don't have unit agreement. My velocities are in hours, but my time is in seconds. Because of that, units won't cancel out the way they're supposed to cancel out, and we won't be able to calculate delta x with the numbers that we're given. So we're either going to have to convert both of our velocities into miles per second, or we can convert our time from seconds into hours. To convert from seconds to hours, we need to know how many seconds are in a minute, how many minutes are in an hour. There are 60 seconds in a minute. There are 60 minutes in an hour. Now, whenever we're moving from the smaller unit to the larger unit, we have to make our number smaller. We do the opposite to the number to the unit. So we're going to a bigger unit, we got to make our number smaller, and the way we do that is by dividing. So to get from seconds to minutes, we would divide by 60. To get from minutes to hours, we would divide by 60. If we're going from big unit to small unit, we're reducing the size of the unit, we have to increase the size of the number. If we're going this way, we would multiply to make the number bigger. So we are going from seconds to hours. We're going from small to large. We're going to have to divide our number here to make it small. So 7.2 divided by 60, divided by 60 again, is 2 times 10 to the negative third, which would be 0.002 hours. The negative 3 tells me to move that decimal point 3 places over the left, so 0.002 hours. You could just leave it in scientific notation and use a number in scientific notation in your calculation. Or if you want to put a decimal form, you could do that too. And some calculators will give you the numbers in scientific notation. Some calculators will give you the number in decimal form. So now that we've done this, we can go ahead and do our calculation. Delta x equals 1/2 VF plus VI times delta t. So delta x equals 1/2 60 miles per hour plus 0 miles per hour times 0.002 hours. This is why we had to do the unit conversion. When we multiply these together, the hours will cancel out and be left with miles, how far the car traveled. If we had left this in seconds, these units wouldn't cancel and we wouldn't be getting delta x. So this is 0.5 times 60 times 0.002. So it's 0.06. And that would be miles, because again, the hours are going to cancel out and we're going to be left with miles. It is a small number because we're dealing with a large unit. If you want to convert that into feet, 1 mile is 5,280 feet. So we would multiply that by 5,280. So 316 feet is what it would be. If you want a different number that's in a unit that you might be able to relate to better, you take your mile answers times 5,280 to convert them into feet. But again, small number because we're dealing with a huge unit of distance. The final thing that comes up in this is having to use old equations before you use the new one. Having to do a calculation of speed, velocity, or acceleration before you can do anything else. These kind of problems are very typical in physics classes where you're trying to come up with some approach, trying to do some other kind of problem solving before you have all the variables you need to use your brand spanking new equation. It's not an uncommon thing. Take a look at an example of one of those. When those cheetahs are quick, they can accelerate at an average at a rate of 20 miles per hour per second. Let's say our cheetah accelerates from rest. Let's say they accelerate for 1.2 seconds. How much ground will it cover? Or how far will it go? So when we look at this problem, we have miles per hour per second. That's an acceleration. And you might be thinking, hey, I thought we were learning an equation that didn't have acceleration in it. Well, that's your clue that we're probably going to have to do this in a couple of steps at least. We are given a time of 1.2 seconds. We're trying to find a delta x. And yeah, there are better ways of doing this problem. The thing is, we're using this one equation. So we have to do this in a couple of steps. We're going to start by using the acceleration equation to find a delta v. That's what we can do with the numbers that we have. Acceleration equals delta v over delta t. My acceleration is 20 miles per hour per second. I'm looking for delta v. My time is 1.2 seconds. So I multiply both sides by 1.2. Solve. My change in velocity is going to be equal to 1.2 seconds times 20 miles per hour per second, which is 24. Seconds cancel, so that's miles per hour. So I know delta v. Fantastic, it's not in my equation, but I can use the delta v equation to find my vf. Vf minus vi. My delta v is 24. I'm starting at rest, so my vi was 0. Vf is 24. So I can add those two pieces of information to my list. Again, using an equation from previous unit to get what we need to plug into our new equation. Not uncommon in physics, happens all the time. Now I've got a VF, a VI, I've got a T. I'm done with this, I don't need it anymore. Those are the pieces of information I need to do my kinematic equation. I don't have unit agreement. I've got seconds and hours again. So I either have to convert this to miles per second or I have to convert that into hours. And the easiest thing to do would just be to convert this into hours. 1.2 times 60 would turn it into minutes. That number times 60 again, or not times, divided by 1.2 divided by 60 will turn that into minutes. Divided by 60 again will turn it into hours. That's 3.3 repeating times 10 to the negative 4. So I'll just round that 0.0003. And again, our rounding is very arbitrary because we're not trying to incorporate significant figures into this. We're just trying to get the concept and the problem solving stuff down. Delta X equals 1/2 VF plus VI times delta T. 1/2 of 24 miles per hour plus 0 miles per hour times 0.0003 hours. Again, making sure those units are the same so that they will cancel out correctly. So 1/2 times 24 is 12 times 0.0003 is 3.6 times 10 to the negative third, or 0.0036. And that would be miles because the hours are going to cancel. And again, it's a very, very small number because it's a very, very large unit. You would multiply that by 5,280 if you wanted to know how many feet that took. It would be 19 feet. It's a very reasonable number. That's it. That's our first kinematic equation. Similar things with the rest of them. Look at how they're derived and then what we use them for.